Alex Summers from the University of British Columbia is talking about Prusti. Go ahead, Alex.
Okay, thanks a lot for the chance to talk about the project. This is joint work with a bunch of people on the slides of Vytautas and Aurel and Christoph and Federico and Peter, all at ETH. So since we're here talking about Rust verification, I thought I'd begin in the wrong language and talk about C. So here is a tiny snippet of C code, maybe the smallest one can write that illustrates an aliasing problem. And here my idea, I guess, is that I've got some fact about a particular list reference, and then I call a method on a different list reference, and I'd like to assert that the fact is still true. And of course, in C, it's not obvious whether this should be the case or not. Various things could go wrong. So I would like to prove this functional property of my code, that this assertion is never violated. But it could be that the code crashes. Maybe here I dereference null. It could also be that because of aliasing, maybe A and B are the same, maybe A aliases B somewhere in the middle of the list, then the property should not hold. It could also be, if I'm in a concurrent setting, that there are data races, in which case it's much more complex to say what this code is really supposed to do. So this is a classical problem, and there are many, many solutions out there in terms of formal verification techniques that try to do modular reasoning about programs. So we reason about calls without inlining their implementations. The basic idea behind many techniques is that you associate some kind of notion of ownership or permissions to particular heap locations. So in other logics, such as separation logic, you'd see a different syntax. There are other approaches that would handle the framing problem in a different way. And then you typically need some kinds of assertions to lift this idea to whole data structures. You want some way to describe, say, an entire linked list at once. And then the power that comes from logics like separation logic is you also have a way to say, I have two assertions in the heap, and they're in some sense disjoint in memory. So I can now describe partitions of the heap. And then typically, if you want to do some kind of proofs in this style, then you need to write some auxiliary annotation yourself. So to give you an idea of what this is like, I thought I'd show you. So this is Viper. This is an intermediate verification language that we've also collaboratively developed. And in Viper, I can code up for problems like what it means to reason about my push method in a setting with aliasing. And Viper, by default, enforces a policy that says I need to explain that I have the exclusive permissions to certain fields in order to be able to use them in my code. So I can try to get rid of my verification error in Viper. Viper is complaining that it's not clear why I'm allowed to read this particular heap location using this notion of accessibility. I can say that I have the permission to access this particular heap location. But this pushes my problem somewhere else, because now to recursively call my method, I need to be able to show that I have the permission to a.next.next, and this problem is not going to go away. And so the way you classically solve this problem in a separation logic style methodology is you would instead define a recursive definition to describe your linked lists and say what a linked list is the permission to access both the next and the val fields of a particular reference. And my definition will be recursive. So if x.next is not null, then I have a recursive instance of the same predicate. And now I can persuade Viper that everything is fine. I'll say I start off with a list and I end up with a list. And Viper is still unhappy because when you reason in tools like these with recursive definitions, you need to give some direction as to how you're unrolling and rolling up these definitions. So I need to say I'm folding my recursive definition here and also at the end of the program. And I also need to get the annotations correct so that I'm folding the recursive definition in the right places. So don't worry too much if this is a little bit opaque and tricky. But I guess the message is this can be done. And there are well-developed logics and well-developed tools for implementing those logics. So you can build a verifier for something like C. But if you scale this up to a large amount of code, you get this kind of work to do all the time. So there's a lot of annotation overhead and a lot of engineering to do in order to construct the proof scripts that explain to the verifier why everything is okay. And so this typically means that these tools are limited to people who are expert in verification. They need to understand some custom logic, these notions of permissions and disjointness. And on the other hand, as you've seen, in order to persuade the verifier that my program is okay, I have to write these annotations. So I have a certain amount of heavyweight work to do just to get started. I haven't even proved anything about what my program does so far. So I'll refer to this notion as a core proof. So this is the amount of work you have to do just to persuade the underlying verification methodology that the program is memory safe, not necessarily to say anything about what the program does, whether it computes the values that you actually want, for example. So now if we look at a similar snippet of code in Rust, of course, the situation is kind of different from in C. So here were my concerns before about whether or not I can easily reason about my assertion. And of course, in Rust, I know a lot from the type system. So I know that I won't get a memory error when I dereference B because of the guarantees of what unmute list means. I also know that these two data structures can't possibly alias anywhere because of the exclusiveness guarantees in the type system. And I know that I don't need to worry about concurrency when I'm analyzing this code. So then the question we asked ourselves several years ago now is, could we somehow also exploit these guarantees to make verification of these kinds of programs simpler? So let me show you what that might potentially look like. And now I need to just quickly fiddle with my VS Code to switch between extensions. So now I'm in Rust. Hopefully this is familiar to most people. I guess most people in the audience have probably programmed in Rust, at least to some extent. So here I've coded up an analogous linked list data structure just to stick with the same example. And now I'd like to write a few functions about the linked list and show you how things work. So here I've got a length function. This is coded up, I think, in the fairly intuitive way. So I recurse. I either get a length 1 if I don't have a next, or I get a length 1 plus a recursive call otherwise. If anyone has any questions about the code, I'm happy to be interrupted. So now I'll write myself a little getter function. So I'd like to fetch elements from my list. And so I'll write a getter that takes an index and returns the element stored at that index. And the way I'm going to write it is I'm going to say, well, if the index is 0, then I'll just give you back whatever self.val is. And otherwise, well, now I'd like to recurse. So the way to deconstruct my list is to match on it. And the case I'd like to write is that some box ref tail, right? This is how we match on the tail structure. This gives me, so now I want to get tail.get at the index -1. So that's how I want to recurse. So if I write this code, then the Rust compiler isn't going to be happy with me because it says, well, why don't you write a none case? This is an option type, so I'm missing a case here. On the other hand, my idea is this none case isn't supposed to happen. Either I've found the element already or I recurse further down the list. So I'll optimistically say this line of code is unreachable. And now instead of the Rust compiler complaining, our tool Pusty is complaining, and it's telling me, well, this unreachable might actually be reachable. And when I think about it, that's the case because I haven't guaranteed anything about the value of this index that I pass in. I could well fall off the end of the list, in which case I would hit this case. So now I can persuade Pusty that everything is okay by, by writing myself a precondition. So Pusty will let me annotate here what it is that needs to be guaranteed every time I call this method. And what I'd like to write is this. I'd like to say my index is always going to be within the bounds of the array. So let's see, sorry, of the list. So now Pusty is a little bit cross with me because it says, well, I'm calling arbitrary code here. So it's not clear that we want to allow for arbitrary Rust code as a specification. In particular, maybe that code could have side effects. But actually, Pusty does allow me to use functions in specifications. I just need to label them as what's called pure. So pure means you can think of this as a deterministic mathematical function of the part of the heap reachable from this reference. It's a question in the chat. Why do I need 0 less than or equal to I when I is unsized? I probably don't. Let me check that. But I may not have configured my particular VS Code instance to, yeah, okay. So there's an option to switch on the bounds encoding for the types, and I think I haven't got my instance encoded the right way. So if I switch the right command line option in VS Code, then I wouldn't need that. That's true. I get that precondition for free. Thanks for the question. Thanks, Alan. Okay, so now Pusty is happy with me too. Both the Rust compiler and the verifier are happy because under my precondition, it's able to prove that indeed my unreachable line is unreachable. So that's good. I can write preconditions on my functions just to illustrate what we can do while I'm here. I can also write postconditions, so I can say something about what is guaranteed when a function terminates. And here I'll go slightly outside of Rust syntax because I'd like a name for the return value of a function. So Pusty calls this result. And for example, I could prove something like the result of my len function is always greater than 0. Okay, so let's go a little further. I'd like to write the push method for my vector. And so that will take a mutable reference to self. And what I'll do is I'll push a value onto the end. So now I'm going to write that in a similar way. I'm going to pattern match on self.next. In the case where I've hit the end of the list, then I'm going to assign to self.next. And what am I going to assign? It's going to be a sum of a box of a list. And the list is going to contain this value, and it's not going to have a next. And otherwise, if the list already has a next, so now I need to write some box ref mute tail, then I'm just going to recurse and push onto tail. Okay, so now I've got my push method. Pusty is happy with that push method. I don't need any kind of precondition because push is total. It works on any list. So now I'd like to say something about what my push method does. So let's start with a relatively simple property. I'd like to express how does push affect the length of my list. So now again, I need to go slightly outside of pure Rust syntax in my specification, because I'd like to be able to say that the length will be whatever the length used to be plus 1. So that I can express the current length by writing self.len. And so the way Pusty allows me to talk about the previous length is we have old expressions, as you have in many verification tools. So an old expression wrapping an expression here says, think of this as evaluated in the pre-state of this function call. So this says that the length is equal to the length plus 1, just to prove that, I don't know, Pusty doesn't just prove anything that I ask it to. If I try and prove that the length is the same, then it will complain and say that that's not true. Okay, are there any questions so far? I'm not watching the chat very aggressively, but I might notice if you ask in the chat. Okay. So now here's the analog of my client code that I had on the slide earlier. And Pusty will also prove that this assertion holds. And again, I mean, just to show that it's actually proving something, if I try to get it to prove something that isn't true, then it won't go through. So, I mean, that assertion doesn't actually require any of these specifications. In that particular case, if I were to go back and delete my various specifications on these various functions, the assertion will still go through here because it follows from the guarantees that we're translating from the Rust type system itself. The fact that B and A can't alias anywhere all the way down is enough to give this assertion. Whereas if I wanted to prove something more interesting about what the values of the list actually are, then I would start relying on functional specifications that I've written on the functions. Okay, so to go just slightly further still, I'd like to be able to say something about what is stored in my linked list after I've pushed. And so one thing I should know is that the last element after I pushed, so that's self.get of self.len -1, this ought to be equal to v. Oh yeah, I saw the question in the chat. Thanks for answering. Yeah, I mean, switching overflow checking on is actually dual. I mean, it would also fix my problem before. Basically, switching on the bounded understanding of integers would fix both problems. Okay, so now Pusty is saying, I'm not sure that get is pure, so I'll just tell it that get is pure. And then it's able to prove this. But of course, I'd quite like to know after calling push, not only that the last element is v, but that all the other elements are still what they were before. And to write this, we'll go a little bit further out of purely Rust syntax. So we'll add a little bit more in terms of syntax, and we'll use a quantifier. So here I'll say, and we use closure style syntax for quantifiers. Here I'll say, if you give me any index between 0 and self.lem -1, then what you'll get if you call get at that index is the same as what you would have gotten if you called it at the beginning of the function call. So now what we have is specifications which are at the level of Rust expressions on the whole, but with a few particular additions. So we have kind of Rust expressions ++ that enable us to write relatively rich functional specifications about the code if we want to.
Question.
Please.
So this way of specifying list content is basically stating the content of the list kind of indirectly by saying what would happen if I called get on the list. Is there also a way I could like think of the Rust list as representing a mathematical list and can talk about how that mathematical value evolves as I do push and how get relates to that mathematical value?
Yeah, that makes total sense. Thanks for the question. We are currently adding support for mathematical types. So right now we just don't have the syntax, basically. There are such mathematical types in Viper, and we map these verification conditions down to Viper, as you probably know. So we're mainly engineering the sort of language level support right now for that.
Okay, I see. So that would give me some kind of, feels a bit like a refinement system there at that point, I guess.
Yeah, I think you'd have several alternative ways of expressing your specification, and one would be to map to a sequence first. Exactly.
Okay, nice, thanks.
Thanks. Okay, so I've shown you a little what this might look like. In fact, this is what it looks like. This is Pusty. Pusty is a tool that takes Rust, and it's actually implemented as a plugin for the Rust compiler, and maps annotated Rust programs down to this Viper intermediate language that I briefly showed at the beginning. And then, of course, we also give feedback back, so you know what's it's able to prove and what not. So the general approach in Pusty is that we're mapping a lot of the type information that comes from the Rust compiler to specifications for free. So these specifications prescribe the ownership part of the proof under the hood in a way that means the user doesn't actually have to manually write those kinds of specifications. In a certain sense, you could say they've written those specifications already just by getting the program to type check. And so signatures of, say, functions get translated to a kind of core pre and post condition, which doesn't say anything about what the function computes, but translates sort of the aliasing guarantees, for example, that Rust gives for free. And then we plug into a bunch of compiler analyses, including actually the Polonius analysis that Nico talked about the other day. And we use this to generate the auxiliary annotations that you've seen Viper requires in order to get the proof to go through. So this is also automated. And then one can add user specifications if you wish. And that translates to an analogous functional specification at the Viper level that augments the core proof with something about what the program actually does. So the idea is then one can stick at this more or less Rust level of abstraction for writing the specifications and for understanding them. One doesn't need to drop into a trickier underlying program logic. So now this picture goes away, and instead of having to write all of these annotations by hand, this is all generated automatically by the Pusty tool. And the users can write their own functional specifications if they wish to say something about what the code actually does, and those will also get pushed through the tool. So the abstraction level stays at this kind of Rust expressions ++, as I said before. I'll assume, unless I'm interrupted, that things are getting answered in the chat. It looks as though that's the case. So the type encoding, just to give you a brief idea, I mean, essentially we read off these predicates of the kind that you've seen me write by hand from the structure definitions, from the struct definitions in Rust. I won't say too much about that. We generate essentially a different predicate type for every type that shows up in the program. At the moment, that includes monomorphizing various polymorphic types. So for example, option box list is really a predicate in the Viper encoding. And that lets us read off an analogous predicate definition that describes the ownership of the heap that you get all the way down in Rust. And then reading off specifications for functions becomes reading off the analogous types and translating them into our predicates. So you get some analogous specification for free in Viper. And if the user chooses to write extra specifications in Pusty, these just get conjoined in all the right places. Okay, it wasn't all quite this simple, and I'd like to at least give you a flavor of some of the challenges we had in the meantime. So it turns out specifying reborrowing in Rust, in particular writing a modular specification for functions that allow mutable reborrowing, is an interesting challenge. And so if you imagine what this does in Rust, if I take, say, a reference to self and perhaps return a reference to the list a certain number of elements down, then in Rust, what happens is I get out a mutable reference to some subpart of the data structure. And then when I call this function, the initial reference is blocked. And so what this means is you can't do anything with the initial reference while the returned reference is live. And then on the other hand, in the meantime, you can mutate via the return reference. And then at some point, the return reference will die. And effectively, those capabilities go back to the original reference, but we'll see the side effects that you've made via the return reference. So to fit this into the Pusty style verification, we needed to find a way to model, firstly, the permissions that are still associated with this currently frozen reference. And we wanted to do that in a way that doesn't necessarily expose paths in the data structure. So we'd like to be able to write this specification so that clients of the function don't need to know how the data structure is implemented. And then we'd also like to somehow add functional specifications that say, what is the combined effect of the side effects that may have already happened when you call this function, along with the side effects that the caller hasn't even made yet via the returned reference. And so just to give you an idea of that, and I'd be happy to talk offline if anyone would like to see more details, we model the permissions part of the story with a construct called the magic wand, which comes from separation logic. And we have a novel specification style called pledges, which is what the user can use to write what's a postcondition on such a function. So a pledge looks something like this. And the idea is instead of specifying how things look right now in terms of the entire list, because right now the list isn't accessible, I can say how will the list look by the time that my reborrowed reference expires. So I can say properties like the length will be, well, it will definitely be at least index long. And then it will be index plus the length of whatever sublist you give me back. And of course, the client might potentially modify the list's length before the reborrow expires. So this gives you full flexibility, again, in terms of how much you want to specify about what will really be guaranteed, but you don't need to know how I actually got to this underlying reference. You don't need to know the structure of the internal data structure. And again, these proofs are all fully automated as well. Okay, so this gets a little trickier. I'm happy to talk a bit more offline if people would like to hear more about that. So here's some evaluation that we did right back when we wrote the first paper. We took the 500 most popular crates. We filtered based on all the functions that we currently support in Pusty. So I think this number would increase now. In fact, we should rerun the evaluation and see. And then we basically checked, can we construct these core proofs where you don't write any specifications at all reliably? And the answer was yes. And this generates roughly 1 million lines of Viper code, but all of this goes through automatically. And then we also did a bit more evaluation on the functional specification side. So we took a bunch of interesting programming examples and we coded up specifications of those for Rust implementations and showed a variety of properties. In some cases, just crash freedom. In other cases, that these algorithms actually compute the results that they're supposed to. And times vary somewhat depending on how complex the specifications are. Some of these have many, many quantifiers, for example, but they all work and they all work in fairly reasonable time. You can see that in some cases there are different versions of the same example. So here we have a version of binary search which just checks for panic freedom essentially and also checks for overflows. And that takes very little annotation overhead and relatively little time, but you need a lot more annotation overhead if you want to show that binary search actually produces the result you would expect. Good. So I think I can stop just about there. So if you'd like to take a look at the paper, which is a couple of years old now, but still gives some details of the basics of this Viper encoding and how we automate the proofs. It also tells you more about this pledges feature that I've only briefly alluded to, but was one of the more interesting specification challenges we had to solve at the time. And tells you more about the subset of Rust we currently support, although that's a little out of date now. So since then, we've supported rather more features. So we have some support for traits and subtyping in Pusty. We have support for more general copy types in specifications. There's the facility to write external specifications on libraries now, which is, of course, very useful in practice. And we have some basic support for generics. And there's a whole bunch more work in the pipeline right now. So we're looking at verification of closures and certain concurrency features. There will be these mathematical types that I mentioned in response to Ralph's question, and also a notion of ghost code coming soon. And we're starting to look at applying Pusty to more serious code bases, including collaborating with a couple of people at AWS, including Rajiv, I think. And so now the library abstractions become a more interesting question, because as we start looking at more serious code bases, it's important to be able to abstract over large amounts of code that we don't want to verify at the same time. And we're nonetheless looking into a little right now how we can start to push into a little of the unsafe space of Rust. Okay, so I think I can stop there. Thanks a lot for your attention. I gave you at least a very high-level overview of the project. There's a lot going on. If you would like to find out more, there's a Zulip chat channel there. There's also a project webpage. So we've given this separation logic style proof kind of for free under the hood. And because it's automated for you, this dramatically simplifies the level of abstraction that one works at. You get to write these specifications that are essentially at the level of Rust expressions, plus a few powerful features that we've designed to enable modular specification. And I'm on the lookout for more students in case you know someone who's interested in collaborating. I'm unfortunately going to have to leave after the break, so I'll be here for one more talk, but then I have to go and teach a lecture. But if you'd like to chat with me about anything, then my email's there. And otherwise, I think many of my collaborators are all here, so they'll be able to answer your questions too. Thanks a lot.
Great. Thanks for that talk, Alex. We have a couple of minutes for questions. Daniel has a question. How do you handle traits?
So the basic idea is you can write specifications on trait functions, and then there's a kind of behavioral subtyping enforced if you also want to refine the specification at implementation side. So at implementation side, by default, you just inherit exactly the same specification. If you want to write something more specific, then there are checks effectively that you, well, these are tricky to get right, that you, I guess, weaken preconditions and strengthen postconditions, loosely speaking. The exact check is a little bit more subtle than that, but that's the basic idea.
Could you use that to also like model something like unsafe traits and the extra requirements they have?
I think for some unsafe traits, you could. Yeah, I think that would be really nice. We've seen some unsafe traits where what's unsafe about them is something much more subtle. Like I return you a reference, but it's very important that you only modify this reference in a certain way or in sync with some other reference. So I think it wouldn't be possible to capture all of unsafe trait, like all the specifications you would like to add for all unsafe traits, but I think you could capture quite an interesting class of them, yes.
So Herman has a question. I think his question is, how do you specify the add trait?
I don't think we have them. I think one of the difficulties, so if I understand the trait correctly, one of the difficulties is some of the specifications you want to write are not just about single states. You want to write things. Let me check what the add trait actually is. Maybe I'm thinking of the wrong one. But are you thinking of one that imposes that we behave like an addition? I'm now looking up the add trait. Right. So I think some of the properties you would want is that the operator behaves, it has these sort of transitivity, these, I can't think of the word, symmetry properties, etc. So to some extent, you can specify these using quantifiers, but in some cases, you'd like to, I think you could actually for add. I think for add, you could really specify everything using quantifiers. You could say that all calls to this function satisfy, say, things like these symmetry properties that you would expect of the operator. Is that the kind of specification you had in mind, Herman? So I think more generally for some of these more abstract traits, one would like to be able to say something about like arbitrary calls that you make to certain functions. So not the call that you're making right now, but essentially all calls to the function. Right, a bit related to what Xavier just posted in the chat, thanks. So we don't have syntax for this right now, but I think we're going to have it pretty soon because it's a bit related to some of the work that we're doing in verifying closures, as it turns out, that you want to be able to talk about general calls to a particular function as opposed to the one that you're making right now. So I guess to write the super nice specs for add, we might need some of those features, which are coming soon, I think.
Okay, let's stop here and let's move on to the next talk. Thanks, Alex.